Well, finally, in lesson 10 of Unit 2, we are getting to the topic of prime numbers. So finally, we can do what a lot of people kind of assume comes first in a number theory course. We can define what a prime number is. So an integer is said to be prime if two conditions are satisfied. First, the only positive factors of the number x are 1 and x, but x has to be at least as large as 2. Now, this second condition can come as a bit of a surprise, but it's actually quite important. It's a bit of a modern addendum to the definition of a prime number, but it is quite universally taken at this point. Specifically, 1 is not a prime number. 1 does satisfy the property that the only positive factors of 1 are 1 in itself, but this second condition that the number has to be at least as large as 2 is really put in specifically so that 1 is not considered prime. Also note that we only asked for positive factors of x, and we only required that x be positive. So we're not going to say something like -7 is prime. No, only positive integers are going to be considered prime, and we're only looking for positive factors when we ask this question. Okay, now for any number n bigger than or equal to 1, so for any positive integer, we define this function tau of n, this is the Greek letter tau, to be the number of positive factors that n has. So for example, tau of 8 is 4. Because the positive factors are 1, 2, 4, and 8, how many factors are there? There were 4 of them, so tau of 8 is 4. Tau of 9 is 3. The factors of 9 are 1, 3, and 9, and there are 3 of them. Tau of 24 is 8. The positive factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. There were 8 total positive factors, so tau of 24 is 8. So this is just a function that counts how many positive factors there are. And the first theorem we'll prove about it is that if tau of n is 1, then n is 1. In other words, the only number for which tau of n is equal to 1 is 1 itself. Well, for any n that's 2 or larger, 1 is a factor of any number, and any number is a factor of itself. So if n is 2 or larger, then 1 and n are different factors of n, so tau of n is at least as large as 2. So the only possibility to have tau of n be smaller than 2 is for n to not be as large as 2. In other words, n has to be less than or equal to 1. Of course, this function was only defined on n bigger than or equal to 1. So the only number that it could even be possible for tau of n to be 1 would be 1 itself. And tau of 1 is 1. The only positive factor of 1 is 1. That's a single factor, so tau of 1 is 1. So the only number for which tau is 1 would be plugging in 1 itself. Another theorem we can kind of quickly show is that a number is prime if and only if tau of n is 2. It's really just rephrasing the definition of prime. The only positive factors are 1 in itself, so there are exactly 2 positive factors. And since tau of n has to be 2, this does prohibit 1 from being considered prime again, because tau of 1 is not equal to 2, tau of 1 is equal to 1. Having defined what a prime number is, we can now define what a composite number is. If n is a number so that tau of n is bigger than or equal to 3, then n is called composite. Equivalently, tau of n being bigger than or equal to 3 means n has at least 3 positive factors. 1 and n are definitely positive factors of n. So for tau of n to be 3 or bigger, it has to have some other positive factor that isn't 1 or n. Also, a number that is 2 or bigger is either prime if tau of n is 2, or composite if tau of n is 3 or bigger, but it can't be both because tau of n cannot simultaneously be 2 and larger than 2. But it has to be one or the other. We established on the previous slide that the only number for which tau of n is smaller than 2 is letting n equal 1. So if n is 2 or larger, tau can't be 1, so it has to be 2 or bigger. If tau of n is 2, it's prime. If tau of n is 3 or larger, it's composite. It's got to be prime or composite, but not both. However, 1 is not prime because tau of 1 is not equal to 2, and 1 is not composite because tau of 1 is not 3 or bigger. So what's the deal with 1? It's a special kind of number called a unit. It is a factor of every positive integer that makes it very, very different from other numbers when factoring is being considered. So it's the only positive integer that is a factor of literally everything else. Okay, in other number systems where factoring can be defined differently, there might be multiple objects that have this property. When we're just doing traditional factoring in the positive integers, 1 is the only number that is a factor of everything else. But it is possible to define number systems and methods of factoring where there could be multiple different items that have this property that they can be factored out of everything. So such things are called units. They are factors of everything. And in abstract algebra, they come up and they're important. They're not considered prime. They're not considered composite. They're their own thing. But we're not really going to get into it. And now we can start talking about prime factors. What we're working towards is something called the fundamental theorem of arithmetic, that every number 2 or larger can uniquely be factored as a product of primes. But before we get there, we have to lay some ground rules. So first, every number 2 or larger at least has one factor, which is a prime number. And we're going to prove this inductively. Observe that our base case is n equals 2. That's the smallest integer this theorem claims to apply to, and we simply manually check. What are the factors of 2, the positive factors of 2? 1 and 2, and that's it. It has exactly 2 factors. Tau of 2 is equal to 2, therefore 2 is prime. Great. Also, 2 is a factor of itself. So 2 has a factor, which is a prime number. Okay, so 2 has a prime factor, our base case is done. Our inductive step, we're going to assume every number up to some n has a prime factor. So 2 has a prime factor, 3 has a prime factor, 4 has a prime factor, all the way up to n has a prime factor. What we need to show is that n plus 1 has a prime factor. Well, n plus 1 might be prime, in which case it's a factor of itself and therefore has a prime factor, and hooray, we finished the proof. But n plus 1 might not be prime. If n plus 1 isn't prime, then it has to be composite, because numbers are prime or they are composite, but not both, as long as we're talking about numbers 2 or larger. So if n plus 1 isn't prime, it must be composite, meaning it has a factor k that isn't equal to 1 and isn't equal to itself, isn't equal to n plus 1. Well, if it isn't equal to 1, it's at least as big as 2. If it isn't equal to n plus 1, it's less than or equal to n. So n plus 1 has a factor k that is in between 2 and n. We don't know if k is prime or composite. It's just a factor of n plus 1. But our inductive hypothesis was that every number between 2 and n has a prime factor. So k is between 2 and n, and therefore has a prime factor. So k has a prime factor p, but k was also a factor of n plus 1. And factoring is transitive, so p, this prime number, must be a factor of n plus 1. Therefore, n plus 1, if it's composite, has a prime factor. N plus 1 is either prime or composite. Either way, it has a prime factor. And we've completed the inductive proof. Every number 2 or larger has at least one prime factor. This is our first step towards the fundamental theorem of arithmetic. All right, next up, if p and q are 2 prime numbers that are different from each other, then they are relatively prime. Recall that the definition of relatively prime came before the definition of prime. We're now kind of showing that they sync up, okay? 2 numbers being relatively prime is somewhat consistent with calling a single number prime. If I take 2 prime numbers that are different from each other, they are considered relatively prime to each other. Well, p is prime, so its only positive factors are 1 in itself. Q is prime, its only positive factors are 1 in itself. P and q are not the same number. Therefore, the only number that appears in both lists of factors is 1. So if the only common factor is 1, then that's definitely the largest common factor. There's your GCD. But now we want to extend that result. If p and q are both primes that are not the same prime number, then in fact any power of p and any power of q are relatively prime to each other. Well, suppose one of the exponents is 0. Suppose p to the 0. P to the 0 is of course equal to 1, in which case I'd be taking the GCD of 1 and something else. The only positive factor of 1 is 1. So the only possible GCD would be 1. So if either exponent is 0, you have a GCD where one of the terms is 1, and therefore the GCD is definitely going to be 1. Okay, so there's really nothing to consider unless we assume that n and m are both positive. And we're going to use a technique called double induction. First, we're going to set n is equal to 1, and it's going to stay equal to 1. And now we're going to induct on m. So for n being fixed at 1, so now I'm only considering p to the first. we're going to induct on M that P and Q to the M are always relatively prime. If that first power is 1, I'm just taking the GCD of P and Q, and the theorem at the top of the page shows that those are relatively prime. So inductively, we're going to assume that P and Q to the M are relatively prime, and now we need to show that P and Q to the M plus 1 are relatively prime. We have this result from earlier in this unit that if A and B are relatively prime and A and C are relatively prime, then A and the product B times C are relatively prime. But we know that P and Q are relatively prime, P and Q to the M are relatively prime, therefore P and Q to the M plus 1 are relatively prime. So now we know that if we have fixed n equal to 1, so we just have P to the first power, then overall I can let the exponent on Q be any positive integer. So now what we've done is we've shown a base case for inducting on n, that for any integer m as our exponent on Q, we now claim for any integer n, our exponent on P, that the two numbers will be relatively prime, and our base case would be n equals 1, and that's now proved. So now let's assume that for one particular n, for any exponent m, P to the n and Q to the m are relatively prime. We need to show that we can increase the power on P by 1 and still have these numbers be relatively prime. But it's really the same argument from before. Q to the m and P to the n are relatively prime. That's our inductive hypothesis. Q to the m and P are relatively prime. That's what we proved earlier in this proof, just a few lines above. Therefore, applying the same trick, Q to the m is relatively prime to both P and to P to the n, so it is relatively prime to the product, and that's P to the n plus 1. So it took a double inductive proof, which can be a little bit much to get your hands around. But what we've shown is that if P and Q are different prime numbers, then any powers of them are relatively prime to one another, which is sensible. What does this have to do with common factors? So suppose P is prime, and it's a factor of two numbers A and B, then it must be a factor of the GCD A and B. This falls right out of Bézou's identity. We can write the GCD as a linear combination of A and B. Since P is a factor of A and a factor of B, by assumption, it's a factor of any integer combination of A and B, specifically that one, the GCD. And that's not really a result that's specific to primes. Any integer x would have this property. If it's a factor of A and a factor of B, it must be a factor of the GCD. We've actually mentioned this before, that any common factor of A and B must be a factor of the GCD. Now we're ready to present an extremely old theorem from about 300 years before the Common Era due to Euclid. It's sometimes considered the oldest existing math proof. This is kind of a matter of semantics and terminology, but it's definitely on the list, that there are infinitely many different prime numbers. Okay, so we know what it means for a number to be prime, but we haven't really addressed the question of which numbers are prime versus not prime. And this theorem states there are infinitely many different prime numbers. Let's assume to the contrary, that we have a finite and complete list of all the prime numbers. So these numbers are all different from each other, they are all prime, and furthermore, any number which is prime has to be in this list. We are assuming that there is a finite list that accounts for every single possible prime number. So I'm going to let capital N be the product of all of these things, and I'm going to let capital M be n plus 1. Since every prime is at least as large as 2, okay, so P1 is 2 or bigger, P sub 2 is at least as large as 2, and so forth, capital N is at least as large as 2, and capital M is even bigger, so it's at least as large as 2. Why am I so focused on a number being at least as large as 2? Any number 2 or bigger has a prime factor. So capital M has a prime factor. We assumed, however, that every prime number is in that list of P1 through Pn. So whatever prime number I found to be a factor of m, let's call it P sub I, and it is in that list. So P sub I is a factor of m. M has a prime factor, I called it P sub I. But since P sub I is in that list of primes, it's definitely a factor of n, because n was explicitly constructed to be a product of all the prime numbers. So if P sub I is a factor of both m and n, it must be a factor of the difference. That's a linear combination. But what is m minus n? Well, since m was defined to be n plus 1, m minus n is exactly 1. So if P sub I is a factor of m, then it must be a factor of 1. but 1 does not have any prime factors. It's only positive factor of itself, and 1 is not a prime number. Okay, so we have arrived at a contradiction, and therefore there cannot be such a list of finitely many prime numbers. Okay, it's worth pointing out this isn't exactly the proof that Euclid came up with. The phrasing and terminology is modernized, but it's essentially the same argument, that there cannot be a list of all the prime numbers that, stops and has finitely many terms. Therefore, there must be infinitely many different prime numbers, and that's kind of neat. And this is one of the first things that was ever concretely proven according to rules of logic that were being devised. It's also a result that people have reproved many, many times over the years. There's a great number of different proofs of this result. Some people collect them like Pokemon cards.